6, 5, 4, 3, 2, 1. Yes, I did pause. No. How did you know? I saw it. Okay. So bad luck. Okay, so today we're going to discuss essentially two things. One thing. So we're going to see the consequence. It's actually a very nice, it could be a title of a book. The consequence of not being ideal. I could write poetry about this. Okay, so we're going to discuss essentially, so we know a lot about ideal gases, right, up to now. So what we are going to discuss using what we know about thermodynamics and Maxwell relations and all these kind of things, we're going to discuss how, what happens when your system, your gas is not ideal. And in particular, when the equation of state, instead of being the equation of state of the ideal gas, is the van der Waals equation of state. Okay? And we're going to discuss some of the consequences. There are many, but I don't have infinite time, so I choose just two. All right, so first thing we know about the ideal gas is that its energy depends only on temperature, right? And in particular is given by Cv times T, which is N times R times T divided by gamma minus 1. Now, statistical mechanics, this is not, what I'm going to write now is not something that you can derive from thermodynamics, but statistical mechanics will tell us that this is equal to 1/2 F times N times K Boltzmann times T, where F is the number of degrees of freedom per molecule of this gas. Okay? You can equivalently write it as 1/2 F number of moles R times T. This is something that is known in statistical mechanics as the equipartition theorem. We will see it essentially in the first or second lecture on statistical mechanics. Now you have to believe me, okay? Okay, so as a first application of statistical mechanics, of thermodynamics, let us compute the entropy function, state function entropy for an ideal gas. This is something we didn't do yet, okay? So, entropy of the ideal gas. Now, ds is equal to, we know, dE over T minus, or plus actually, P over T dV minus mu over T dN. This is something we found in the last lecture, okay? One of the last things we wrote down in the last lecture. So let us now introduce in this expression, the expression for the energy of the ideal gas. So since we're using temperature, volume, and number of particles as our variables, we will have 1/2 F times K Boltzmann times d n T over T plus P over T dv minus mu over t dn. And this is going to give us, if you do this differential, so you're going to have t dn plus n dt, is going to give us 1/2 f n k Boltzmann dt over t plus, now here we can use the equation of state of the ideal gas. So P over T is equal to n times k Boltzmann divided by the volume. So this is n times k Boltzmann dV over V plus, and then we are going to have 1/2 f k Boltzmann Fk Boltzmann minus mu over T dn. Okay. Now, if we fix now the number of particles, we see that the differential ds at fixed number of particles can be written as 1/2 f k Boltzmann times n times the differential of the logarithm of t plus n k Boltzmann, the differential of the logarithm of v. And that is because we have this dv over v and dt over t. Okay? Great. So now what do we do with this? We integrate. And if we integrate, we obtain easily that the entropy function, which is a function of temperature, volume, and number of particles, is necessarily going to be equal to 1/2 f k Boltzmann n log of t plus 1/2, sorry, not 1/2, plus n k Boltzmann log of v plus some function that depends on n, which is undetermined. It's arbitrary, right? Doesn't really matter what it is. Now we have to fix this function with one requirement. And what is the requirement we have to satisfy?
It has to be extensive.
It has to be extensive. You have already seen this derivation. Okay, so it has to be extensive. Entropy is extensive. So, since entropy is extensive, let's see the first term. This term here, is it extensive?
Depending on n, yes.
Yes, it depends on n. This one, is it extensive?
Yes.
Yes.
No.
Because of the...
No. No, it's not extensive. It's super extensive. Why? It increases faster than n. Why?
Because it has a logarithm of volume.
It has a logarithm of volume, right? Volume is extensive, so this is n log of n, if you want. So it's not extensive, this term. It's very bad. So how do we cure it?
With the phi.
With the phi. And what do we have to do to the phi in order to cure it? You have to choose it in such a way as to have phi of n, equal to a constant, an extensive something, minus n k Boltzmann log of n. Because if we choose it this way, then you see that we can get at the end that our S of T, V, and N comes out to be 1/2 f K Boltzmann n log of T plus n K Boltzmann log of V over n, because I have this phi n, I chose this phi n, plus A times n. Okay, so this is extensive. Now, here I have the temperature, which is an intensive quantity. Now, for the ideal gas, it turns out that I can trade temperature for internal energy, right? Because since the energy depends only on temperature linearly, I can write everything in terms also of internal energy itself, right? So in particular, I can write my temperature, T, as internal energy divided by 1/2. Is it raining? Oh, too bad. Of K Boltzmann times n.
I'm trying to understand what you said about the n K Boltzmann being here. I still don't.
You don't see it? Well, this is not extensive, right? Because to be extensive should be linearly proportional to number of particles. And the volume is proportional linearly, is an extensive quantity, so therefore this goes like n log of n, because the volume goes like n. Okay, so it's not extensive, too bad. How do we do it? How do we cure it? We just subtract, phi of n is arbitrary. So we choose phi of n to be some linear function of n minus n log of n. This term here will combine with this one to give us this. You see it? Because I will have nk Boltzmann log of v minus log of n, which is log of v over n. Clear? Clear or not clear? I can repeat 10,000 times, I'm here for that.
Yeah, so how does this solve the problem?
How it solves it? Well, now v is proportional to n, right? So this is the volume per particle, which is an intensive quantity. You see? So here I have n, which is extensive, times the log of an intensive quantity. Here I have extensive times the log of temperature, which is intensive. So it solves it fully. Okay? Great. So now I can write the energy this way, which is, by the way, equal to 1/2 F times K Boltzmann to the minus 1 times E over N. And if I now combine this writing with the previous expression, I will obtain our final formula, which is S of T, V, and N equal to 1/2 F N K Boltzmann times the logarithm of E over N plus N K Boltzmann log of V over N plus A times N minus 1/2 F N K Boltzmann log of 1/2 F K Boltzmann. And now you see that all these terms are all proportional to n times something intensive. And therefore I can combine all these terms to write down something like 1/2 F N K Boltzmann log of E over N plus N K Boltzmann log of V over N plus B times N, where B is equal in this case to A minus 1/2 F K Boltzmann log of 1/2. Okay? So this is the entropy of my ideal gas. Yes?
Question. Why in this equation it seems like the number of particles have the units of energy and the units of volume at the same time?
Number of particles as units of energy.
The logarithms.
Ah, this is a very good point. Now, strictly speaking, whenever I integrate this in the log, I should get dimensionless quantities, right?
Yeah.
So I should get a T over T naught and a V over V naught. Okay? So, but V naught is fixed. So V naught is our reference zero temperature, well, our reference point. So that will normalize the units. I'm neglecting to write that.
In the limits of integration of the...
Yeah, the limits of, it's in the
Okay.
limits of integration of this differential, so I'm neglecting that just for simplicity. But it's a good point. It's a very good point. Now, before moving on with other stuff about non-ideal gases, let me tell you something. Let me make you notice something. Let's go back to this formula here. This one. Copy. Okay, so when we look at this formula, we noticed that we fixed our phi of n in order to get this equal to A times n plus minus n k Boltzmann log of n. Okay? Now, notice one thing, that when n is very large, whenever you see an n log n, you think about log of n factorial, right? In particular, you know that log of n factorial is going to be equal approximately in this limit to n log n minus n. And therefore our phi of n could be equally written in this limit as minus k Boltzmann log of n factorial plus n times a minus 1. Okay? In this limit, in the limit of large n. So this implies that our entropy could be written as n k Boltzmann log of V. Let's neglect for a second the term that depends on that. So it's going to be something that depends on temperature. Let's write it like this. Something that depends on temperature. So n times a minus 1 plus some function of temperature, which turns out to be a log of T, plus, let's see the dependence on volume, n k Boltzmann log of V minus k Boltzmann and minus k Boltzmann log of n factorial. Okay? And all of this can be combined into some constant term. Plus k Boltzmann log of v to the power n divided by n factorial. Okay? Now, this formula here is, I believe, and I'm pretty sure, what inspired Boltzmann to write down this famous formula that connects the entropy, we'll see it next time, the entropy to the log of the total number of configurations a system can have at a given entropy, right? Why it inspired Boltzmann? Because suppose that I ask you to solve the following problem. I have an ideal gas of non-interacting particles, which are indistinguishable, cannot be distinguished, and I have to put them in a volume which is divided into cells, right? I have to put them in a volume which is divided into cells, and they are all indistinguishable, right? And I have n such particles. Now, it turns out that the number of ways I can put them, place them at random in this volume is going to be proportional to v to the power n, to the volume. It's actually going to be proportional to the volume divided by the volume of each single cell to the power n. Okay? And then, since they are indistinguishable, I have to divide by n factorial because I don't care about permutations within a single configuration. I'm not labeling each one of these particles. So in practice, this v to the n divided by n factorial is the number of ways I can place these particles inside the volume. And that is the connection between statistics, if you want, in a very basic way, the connection between statistics and thermodynamics we were looking for. Okay? So that's why statistical mechanics starts from this formula. We'll see it next time. Is it clear? Okay. But now we forget about statistical mechanics. We are not yet there. I just wanted to tell you this point because I think it's important. So I'm going to eat, well, as a prize to myself. And now we continue our story on the non-ideal gases. So one of the basic things of ideal gases is the fact that the energy depends only on temperature, right? And it does not depend on volume. Now, in general, sorry. Now, in general, if you have an ideal, a non-ideal, or a generic gas, let's say internal energy, is going to be an extensive function, because it's extensive, right? So it's going to be proportional to n, multiplied by some function of temperature, and of, cannot be a function of the volume itself, otherwise it will not be extensive. It's going to be a function of the volume per particle, which is an intensive quantity. Okay? Coming back to the point. Now, how does it depend? How does the energy depend on the volume in general? Let's compute the derivative. Now, since I'm considering as my variables temperature, number of particles, and volume, which potential should I use in order to compute this derivative? Which one is the thermodynamic potential in which I fix the number of particles, the volume, and the temperature? What? Helmholtz. Correct. 1 point to the guy in the back. Helmholtz free energy. Come on, guys. It's the basic thing. Temperature, volume, number of particles, canonical ensemble, Helmholtz free energy. This should stick to your mind. Okay? Whenever you use temperature, volume, and number of particles, is Helmholtz free energy. Okay? So, and Helmholtz free energy is defined by F equal to E minus Ts. Therefore, E is equal to F plus Ts. And now I have that this is going to be equal to dF dV constant Tn plus T ds dV with constant T and N. Now dF dV is equal to what? What is it going to be?
Related to pressure.
the pressure. It's going to be minus the pressure, actually, if you keep the signs correct. So it's minus P plus T ds dV. Now, how do we calculate ds dV? Any idea? It's hard, right? So we might want to connect it to something a bit more physical or standard that we can measure easily. What can we do?
ds by dv, dE by dv.
ds, we have ds by dV.
It has to be intensive.
Pressure, quantum function.
It has to be intensive. So let's think for a second. We have ds by dV. So what we can do is, for example, so who is conjugate to S?
Temperature.
Who is conjugate to V?
Pressure.
Pressure. What do we do?
Pressure.
We use the Maxwell relations. So conjugate to volume is pressure. So we're going to have dP. Conjugate to entropy is temperature. We're going to have dt at constant volume and number of particles. Okay? Maxwell relations. You see how useful they are? Because ds dN, who knows how to compute ds dV? Unless you do the calculation. Well, in principle we know for the ideal gas, but for the non-ideal gas, it's complicated. So, and now we use T times dP dt constant Vn. In principle, this is something we can measure, how the pressure increases with temperature. For example, you can do it with your mocha, right? How the pressure increases with temperature. Okay, so now we can get this formula. So here we got it using Maxwell relations. We can get it in another way. So this is one derivation. Let me show you another derivation. We can use dE equal to TdS minus P dV minus mu dN. And then we will have, as usual, ds equal to ds dt plus ds dv plus ds dn. Now, if we substitute this up here, right, we will get that our dE is equal to T ds dt constant Vn dt plus minus P plus T ds dV at constant T and N dV plus or minus mu plus T ds dN at constant T and V dN. Now we use again the Maxwell relations. So we'll get T ds dt V. Now if you use the Maxwell relation for this, you get some, T is the conjugate of S, right? So you get that this is equal, you cannot use a Maxwell relation for this. It doesn't make any sense. Plus minus P, here we use the other one that we had. So it was dP dt volume N dV minus mu plus T. So what are we going to get here? ds dn is going to be d mu over dt. Yes, d mu over dt. You have to be careful about the sign. That's the only thing you have to care about. And d mu over dt vn. And now we just read off. Well, dv constant t and n is going to be, again, as we found before, minus p plus t dp dt vn. Okay? It's just a matter of transforming derivatives into something useful. Now, for the ideal gas, what do we get? If we compute this object here.
It's just N or over V.
Is just what?
We just use the state equation for.
Yeah, we just use the state equation. So P
Zero,
times
zero,
P,
zero.
we get 0. We get 0. We know that we should get 0, right? So thermodynamics is correct. Lucky. Equal to 0 for the ideal gas. Actually, is going to be equal to 0 for any system which has an equation of state in this form: P equal to T times some function of V over N. It doesn't matter which function. Because you see, if you take a derivative with respect to T of this pressure, you're going to get, you're going to eliminate this, and then you're going to multiply by this, you're going to get the same as minus P. So this is always going to be 0. So not only for the ideal gas, but for anything that satisfies an equation of this type. Okay? So, now what about, let's see what happens when you can instead something a bit more trivial, a bit less trivial, like the van der Waals equation of state. So this is the acronym for van der Waals equation of state. Okay? So the van der Waals equation of state, we remember, is P times A, P plus A divided by V squared times V minus P equal to R times T. Okay? I just had to think about one thing. But V is essentially equal to V over N. Is the volume per particle. I have to be careful here. I think it's not the volume per particle, but is the volume per mole. Okay? So is that, because you see the way I wrote it, so there is a mistake in my notes. This is the volume per mole, because here I used R, right? So if I put here a K Boltzmann, then this is a volume per particle. If I put here an R, is a volume per mole. Okay? Great. So now, what do we get for the what is the dV for the van der Waals gas? Well, this is going to be minus P plus T dP dV. dP dt, sorry. Now, P is equal to R times T divided by V minus B minus A over V squared. Right? And therefore you see, first of all, you see that it's not in the same form as that bad form that I wrote down before. So it's not going to be equal to 0, right? Because it's not t times something. And second, if you take these two derivatives, you will get that this is equal to a over v squared. Well, which is, by the way, also equal to the derivative of the energy per mole divided by the volume per mole with respect to the volume per mole, right? If I divide both energy and volume by the number of moles, I will get this. All right, so now if I integrate this equation, this one, what do I get? I get that my energy, which is a function of t and v, is going to be equal to minus a over v plus some function of temperature, which is not specified by this equation. Okay? This is going to be the expression for my energy by integrating this object. So now, with this expression of the energy, I can compute, for example, various things like the specific heat, the heat capacity per mole, which is going to be d epsilon dt at constant volume, and is equal to just omega prime of t. Okay? And then I can compute the heat capacity per mole at constant pressure, which is going to be d epsilon d T at constant pressure plus, as we derived a few lectures ago, plus P dV dt at constant pressure. Now, this is equal to omega prime of t minus the derivative of a over v with respect to t plus p dv dt. And now if I take this derivative, I will get that this is equal to omega prime of t plus p plus a over v squared dv dt at constant pressure. Now I have to compute dv dt at constant pressure. Now the way I do it, I take the equation of state. Let me take it here. So I take the equation of state, this one, and I notice that on the right hand side I have, if I take a differential on the right hand side, I have r times dt. And therefore, if I want to compute derivatives of something with respect to temperature, like this one, it's convenient to just differentiate on both sides this equation of state and see what comes out, right? So if I do so, I will get r dt equal to p plus a over v squared dv plus v minus v, and then I have dp minus 2a over v cubed dv, and that's it. So if I collect all the terms, I will have p minus a over v squared plus 2ab over v cubed dv plus v minus b dp. Okay? So Now it's straightforward. What is dVdt at constant p? dVdt at constant p is equal to r divided by p minus a over b squared plus 2ab divided by v cube. Okay? So now that we have this expression, which might be complicated, but I mean it's quite useful, we just plug it back in here. In here, in this one, and we're ready to compute what is the result. The final result is, don't fall asleep, because now we're getting to some physics, okay? So I know that the calculations are boring, but we'll get to some physics at the end. Result is Cp equal to omega prime of t plus p plus a b squared times r divided by p minus ab squared plus 2ab over v cube, which can be written in a simpler way as omega prime of t plus r squared t omega cube, sorry, not omega cube, v cube, divided by r times t times v cube minus 2a v minus b squared. So this is Cp. Then Cv is equal to omega prime times t. Now, when you're given a result like this, okay, the first thing you can ask yourself is, the calculations are so complicated. Are they correct? So how do you check?
A and B zero.
A and B zero?
And
Okay,
then it's
that's one possibility. A and B zero, you will get the equation of state for the ideal gas. So if A and B are zero, what you should get is that the difference between Cp and Cv is equal to R. Do you get it? Yes. What is another limit that you can check? Think about the physics.
If
When is the ideal gas? When is a gas ideal?
if the density is low, it means that
Which means that the volume per particle?
it has to be nearly zero. So
No.
I mean infinity.
It has to be infinity. Each particle lives in an empty universe. Okay? The ideal gas. So do we get it? And the volume goes to infinity. When little v goes to infinity, do we
Yes,
get it?
because in the denominator, the first term is v cubed, the other is v squared.
Absolutely. So we
And
get
they
it.
cancel out.
Right? So you see, in the two limits that matter, we get exactly what we got for the ideal gas. Now this tells us two things. The first thing is that our result is most probably correct. And the second thing, it tells us what should be omega prime of t. Right? Because omega prime of t does not depend on volume, right? So therefore, if we take the limit of v going to infinity or of a and b going to zero, whatever, we should have the same as the ideal gas. And therefore, we should have that omega prime of t is equal to, from the formulas that we wrote down, 1/2 f times r. Okay? So this is what you will get for the van der Waals gas. Now, before we finish, today's lecture, so we still have another 20 minutes, hopefully, maybe less. We'll see, depends how fast we go. Let us do the following exercise. So we have seen that if the ideal gas, if we have an ideal gas and we have the free expansion, right? The temperature is constant and internal energy is also constant, right? This is something we have done, I think, yesterday. If you take a free expansion of an ideal gas, the temperature doesn't change. This is Joule experiment. Now, what about a non-ideal gas? If you let a non-ideal gas freely expand, which means that you had it compressed in a volume and then you remove this volume and you let it explore a larger volume, what is going to happen to the temperature?
It will drop.
It will drop. That's correct. It's going to drop. It's going to drop.
Because there's less interaction between the particles.
Absolutely. That's absolutely correct. 100% correct. There is less interaction between the particles, and therefore, you know, the energy will drop and the agitation will drop, everything will drop, including temperature. As you increase volume, you will tend towards the ideal gas limit. So, therefore, we might want to compute by how much the temperature drops for a non-ideal gas, okay? So we have a gas which is compressed in a certain volume. So this is V initial. As we have done yesterday, this is going to be V final. And now we want to compute the difference delta T, which is equal to integral V initial, V final of dV, dt, dV at constant energy, right? Because the internal energy doesn't change. If you cannot exchange energy with the external environment, right, the internal energy is not going to change. So if you have a free expansion within an thermally isolated container, internal energy will not change. What is going to change is the temperature. All right. Now, how do we compute dt dV? Now, there is a trick that you don't know, but I know, and I'm going to tell you right now, that consists in the following. If we have any three thermodynamic variables, you remember that for all the potentials, we always have three guys. Temperature, volume, pressure, this and that, blah, 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 and so on and so forth. So any three thermodynamic variables, you can do, so let's call them A, B, and C. Then the following relation, which is known as the chain rule, is valid, which tells you that dA, dB at constant C, dB, dC at constant A, and dC, not dA, dU, dC, dA at constant B is equal to -1. Okay? This is the chain rule. It's very useful. It's a theorem in mathematics. Go to Wang, to the book of Wang, and there is a proof of this theorem. So I don't want to waste time. I mean, just keep it as a Wikipedia statement, okay? So this is our chain rule. The second useful thing is that when you have dA, dB at constant C, this is equal to 1 over dB, dA at constant C, okay? So it's an inversion formula. So let's try to apply this formula to our dt dv at constant energy. And this tells us that dt dv at constant energy should times dv dE at constant temperature times dE dt at constant volume should be equal to -1, right? And therefore this implies that dt dv at constant energy is equal to -1 divided by dV dE at constant temperature, dE dt at constant volume. This is equal to, I use now the second rule, this one, for this term here, to write it as minus dE dV at constant temperature, right? Divided by dE dt at constant volume. Okay? And now you see something very interesting, which is the following. What is dE dt at constant volume?
See.
This is CV. So this is equal to -1 over CV dE dV at constant temperature. Now, dE dV at constant temperature we already calculated, right? A few minutes ago. So this is going to be equal to 1 over CV times P minus T dP dt at constant volume. All right? Now, for the van der Waals gas, van der Waals equation of state, then we're going to get the following. We already calculated what is minus P plus T dP dt before. So we're going to get that dt dV at constant energy is going to be equal to 1 over CV times minus A over V squared. Okay? Clear to everybody? And now we know what is CV. CV is equal to 1/2 Fn times R, okay, where N is the number of moles and R is the ideal gas constant. Therefore, we can plug this in the integral that I wrote down before, this one, and just do the integration. And the result is going to be the following, that delta T is equal to minus 2A divided by F times R times the integral between V initial and V final dV 1 over V squared, and this is equal to 2A.
We need N also.
N? No, I don't need N. Because you see, here there is a dV. You see this dV here.
Ah, yeah.
And the N goes to change to the change of variables that make this become a d little v.
Yeah.
So this is a molar volume. So this is going to be F times R times 1 over V final minus 1 over V initial. And this is great because it tells us exactly what we wanted to know. It tells us that if I have a final volume which is greater than the initial volume, so the gas is expanding in a thermally isolated environment, then the temperature is going to drop in general. You see that everything depends on A. If A is equal to 0, then that's it. You're back to the ideal gas. You're back to the ideal gas. Or if the volumes are very, very large. Okay? The molar volumes are very large, you're again back. The differences are going to be very small. All right, so today we had a super short lecture. I apologize, but I prepared it yesterday, and that's all I could, all the material I could manage to redo for today. So next time we are going to see something about phase transitions, something short about phase transitions, and then we're going to pass to statistical mechanics. Okay? And that's it.
This result doesn't depend on B.
On what?
On B, but I'm trying to see like a physical explanation.
If there is an explanation why it doesn't depend on V. On B. I think it's probably because the excluded volume is the same when you have a free expansion, right? If you think about it, right? I mean, if I am in a small volume or in a large volume, the excluded volume is always the same. We think might be related to this. I don't see any other reason. I never thought about this. It's a good question.
B is the excluded volume.
B is the excluded
and
volume.
A is the
A is the long range, is the tail of interaction. So it's natural that as you increase the distance, the average distance between particles, this tail is going to matter, right? It's going to see this average distance.
It's like effective volume of each particle. Can be.
No. Yeah. So each particle has an excluded volume, a hardcore excluded volume, which is set by B.
Yeah.
And then there is a long-range tail, an interaction, whose strength is set by A, right? So what I'm saying is that if you increase the distance, the average distance between particles, the excluded volume is always, a short-range type of interaction. But this longer range part is going to see this average distance is increasing. While the excluded volume in the smaller volume or in the larger volume is going to be more or less the same, I think, unless you go to extremely high densities and you try to pack your particles, but then they will become solid before you manage to pack them.
Is the excluded volume the function of number of particles?
Yes.
In the van der Waals equation of state is not, because it's the excluded volume per particle.
Okay.
Here we are keeping the number of particles fixed. So when you see when I write the equation of state in this form, so V is the volume per mole. So this is the excluded volume per mole, if you want. So if I write this with a K-Boltzmann here, I will have to write everything in terms of n, the total number of particles, and then B is going to have the meaning of excluded volume per particle. But it's more or less the same thing, right? Now, of course, the total excluded volume depends on the total number of moles or on the total number of particles. But here in this process of free expansion, we are keeping the total number of particles fixed. So the excluded volume is always the same. And what changes is the average distance between particles, which is controlled indeed by this part here in the equation of state, this one. Okay? So that's my explanation for the moment. If you find something better.
Is there any parameters that affects the B? B.
Well, the type of molecule the type of molecule affects B, because it's a, you know, eventually when we will derive this using statistical mechanics, I don't have formulas with me. Let me see, maybe I have them in last year lecture notes. So just a second. No. Here. Yes. So you see, well, so this A depends on omega, and omega depends on the radius of interaction. It depends on the parameters of the type of interaction between particles that you have, and that's it.
If we are considering a non-ideal gas, where the only thing that we care about is the collision of hard spheres, so the excluded volume will be...
No, it's not just a collision of hard spheres. Look at this potential, right?
Yes, I mean, if we...
You have a hardcore part that
Yes.
sets this parameter U naught, and then you have this long range term that is long range, whatever, that decays, whose length scale is set by this parameter R naught.
Yes.
And it turns out that in your constants, look at what is the definition of omega, you see that R naught appears here, and your A and B depend on U, that is set by the short range part, and on R naught.
Yes, of course.
So, depend on both.
If we take U0 equals to 0, we will have only collisions of hard spheres with a radius of...
If you get, sorry, R naught is the parameter of, R naught is this,
Size of the-
thickness, is
yeah,
the size of the
molecule.
hard sphere, and U naught is the parameter of the decay interaction. If you take only hard spheres, then you're going to have U naught equal to 0,
Yeah.
then A is going to be equal to 0, and the only thing that remains is B,
What is
the
the...
excluded volume.
Oh, I'm not really familiar with it, but what is the internal energy equation for the non-ideal gas?
What is the internal energy equation for the
Non-ideal.
non-ideal gas? Well, this is something that you can calculate, right?
Yes, but
Let's see.
just to get the answer at this point.
The internal energy for the non-ideal gas is actually, we calculated it. Where is it? Just a second. So this is the answer. And omega of t, you just fix it because you know what is the derivative.
Yeah.
We calculated it before by fixing Cv and Cp. So then, therefore, you know what is also the internal energy. And that's it. So it's the same of the ideal gas minus A times V. Okay? So anyway, the summary. A depends on, B depends only on the short range part of the interaction, and is hardcore part of the interaction. BA depends on the strength of the long range part of the interaction between molecules and on R naught. If you exclude the long range part of interactions and you have only hardcore spheres, you're going to have just an excluded volume and nothing else. Okay? Clear? Look, guys, I gave you a toy. I mean, now you can play with it. Right? I mean, you don't. When I was studying statistical mechanics, I was not given these toys. So enjoy.